Hi, hello everybody. We're going to continue on with chapter 6. We have two more sections left to go. We're going to cover 6.3 today. Work and energy using varying forces. Now, I want to make a note. We're only covering parts of this section because some of it involves concepts with integration, which you guys have not yet gotten to in calculus. So some of the derivations of some of the formulas that are in this chapter takes that, so we're kind of just going to throw formulas at you for now, maybe come back to the proofs at a later time. And also we're only going to do the examples that include algebra in this section, not any of the integral calculus. Alright, it all starts with springs and discussing them right now. Unfortunately, if we're in class right now, just prior to this lab, we do a lab on something called Hooke's Law. So it's like to introduce you to it. Since we're not present to be able to do that hands-on lab right now, but hopefully we will at a later time, I'm going to use a simulation which does at least a small amount of what that lab would do. Now a spring is it takes a varying force to stretch or compress it. So if I just put a X amount of force and stayed at that force, like 66 newtons down here, you can see in the slider, an applied force, I would stretch it so far and that would only get me so far, and unless I changed my force, it would just stay there. To pull it harder and stretch it more, I'd have to up that force. So you notice the slider, as I stretch, it takes a bigger force, so the force varies with this stuff going on. So Hooke's Law is the simple formula F equals kx. There's actually often a negative on it for reasons I don't even really want to get into right now. Let's worry about magnitude overall right now. And just note this equation known as Hooke's Law, Hooke being the last name of the guy, is a force required to stretch a spring. Actually, it's also would work for compressing a spring as well. Where K is a new variable, it's known as a spring constant. And X is the distance stretched or compressed. So if we know the spring constant and the distance stretched or compressed, if we multiply them, Hooke's Law tells us that should equal the force. Now, little thing here, what is the spring constant? Kind of a big thing. It's a value that the higher it is, the more difficult it is to stretch or compress the spring. The lower it is, the less difficult. And it's based on a physical characteristics of the spring. What it's made out of, maybe how large the coils are, things of that nature that would affect its tightness or looseness, I guess is a way you could think about it. So, right now I have this simulated spring with 0 newtons of force on it, so that means it's at equilibrium. This is where it naturally is. This spring is able to stretch or compress. Some springs are only stretchable, and when they're at equilibrium, they can't compress anymore. This spring could go either way. So I'm going to stretch this spring 0.269 meters. And here's the spring constant that's listed in this simulation. So Hooke's Law is pretty simple. It just says if I multiply this displacement, whether it's a stretch or compress, it doesn't matter, times the spring constant, that should equal the force necessary to stretch it, which I could put here. It's the same one that's on the slider, 70. I could put it as a vector up here, 70 newtons. So if I simply multiply 260 times 0.269, I should get about 70 newtons. I do, 69.94, which in sig figs goes to 70 for this situation. So for the time being, there's not much more to say about Hooke's Law. But there's a formula for the work, since this chapter is all about work. If we want to find the work done to stretch a spring, it's equal to this formula, 1/2 kx2 squared minus 1/2 kx1 squared. And individually, 1/2 kx squared, either one, kx2 squared or kx1 squared, is the energy of a spring, okay, once it's pulled a certain amount. So this actually originates a lot like the work energy theorem with the change in kinetic energy for just a normal particle object in section 6.2. But this is specifically defined as a work done to stretch a spring from one position to another. If x1 is the equilibrium position, then this whole term is 0. I just want to make a note, even though we're learning some new formulas, in conjunction with these new ones, we can still use the work total formula for the work from the basic work energy theorem from section 6.2. It's still applicable even with varying forces. All right, so let's jump into, well, to start, a real simple example, the work done on a spring scale. It's for the work done on a spring scale. This is on page 185, by the way. It says a woman weighing 600 newtons steps on a bathroom scale that contains a stiff spring. In equilibrium, the spring is compressed 1 centimeter under her weight. Find the force constant of the spring and the total work done on it during the compression. All right, so we're given the force needed to compress it. We're given the distance compressed, and it started from equilibrium. To figure out the total work, that's this formula, but we don't have the spring constant. But because of the force and the compression given, I could plug into Hooke's law to solve for K and get 60,000 newtons per meter. That's the typical unit we want K, the spring constant, in, newtons per meter. As long as our forces are in newtons and our stretches or compresses are in meters, that's what will come out. Now that we have that, we can plug into the work done by a spring formula. Work done to, well, I'm sorry, let me redefine that. Work needed to stretch a spring formula from above. Work done to stretch a spring. Plug into that, and we get 3 joules. Remember, a joule is a Newton meter. Work in all energies, we like in joules. So hopefully that was a pretty easy example. Now let's get to one where we use the old work energy theorem along with this new work total on a spring. All right. So I want to again stress before we start this problem, the formula here is the work total on a spring. All right. Then whatever the spring is attached to that's pulling on it would be the spring on the object. So we have a Newton's third law thing going on. And let me show you with the example before we start. So the work for me to pull on this spring is negative 90 newtons, excuse me. If I put a vector on for the spring force, the spring's pulling back on me in the opposite direction at 90 newtons as well. That's like a Newton's third law thing going on, equal and opposite, right? If I'm pulling on the spring, or this apparatus is pulling on the spring with 90 newtons to the right to stretch it, the spring would be pulling back on it with 90 newtons in the opposite direction. We need to keep that in mind to understand direction throughout this next example. So there's a good diagram, this is on page 186, of an air track glider hooked to a spring. And this 1.1 kilogram glider in example 6.7 is attached to this spring whose force constant is 20 newtons per meter. Initially the spring is unstretched and the glider is moving at 1.5 meters per second to the right. Find the maximum distance d that the glider moves to the right. In other words, we want to find the distance the spring stretched, and they want us to call it d. Okay? And we want to find it first for part A, if the air track is on, therefore we can ignore friction, and then in part B, if we turn it off and there is friction. All right, so first we're going to set up the formula for the work total on a spring. And that's our new formula from above. It did start from equilibrium. It told us that. It was unstretched. So this whole part's 0. And it's going to stretch to some position x2 that we define in the formula. However, this particular problem is just having us call x2 distance d, distance stretched. All right, so I'm just substituting that in. If it didn't tell me, if it just said find how far it was stretched and didn't tell me to define it as variable d, I could have kept it x2. But anytime we're given defined variables, we should use them. So that's the only reason there's a substitution here. So since this whole term 0, this is the work total being done on the spring by the glider. Now let's look at the glider itself with the basic work energy theorem of the change in kinetic energy. 1/2 mv final squared minus 1/2 mv initial squared. Initially it's moving at 1.5 meters per second. But this, once it stretches the spring some maximum distance d that we defined up here, it'll come to a stop. So that's why this whole term's 0. And now we just got to be careful. I'm going to explain what this little note means below. Right at this moment, this expression means the work total being done on the spring. And this one means the work total being done on the glider. But remember what I said, that equal and opposite thing. The work total on the spring is equal and opposite to the work being done on the thing attached or pulling on the spring, which is the glider, just in the other direction. So I just need to take it in that other direction, and therefore I could set these two expressions equal. If I make this expression negative, it now becomes the work total of the spring on the glider, not of the glider on the spring. Remember, straightforward, this is defined as the work done on the spring. If I make this a negative, that will be the work done of the spring on the glider. And that's for the same reason when I flip this on here, right? It goes both ways, just different directions. So if I do that, these both are two separate formulas which represent work on the glider, so they could be equal. As long as I make that top one negative, and I set it equal to this expression we got down there from the work energy theorem, and now I could solve it for D. Flop it around, and it stretches 0.106 meters. Now part B tells us to include friction. And the mu k is 0.47 for the friction. Now we should remember from the past that friction, kinetic friction, equals mu k times the normal force. For this glider, since it's on a flat surface with only horizontal pushes or pulls, it's equal to, the normal force is equal to the weight, and the weight's mg. So the work done by friction has to be included with the spring. All right? So this expression here from above still holds true, because that's the work total by the change in kinetic energy from the work energy theorem. That's still true. But we need to realize the glider, the total work on the glider, is being affected by the spring and friction. Well, we just transfer the spring. Remember, we had to make it negative. So this represents the work of the spring on the glider, not the glider on the spring. So we still make that negative for reasons we described above. And it has, so there it says right there, and it has to be added to the work of friction, which, remember from past sections, we learned that friction always does negative work. That negative just didn't come out of thin air. If the glider is moving to the right, the force of friction is to the left, making the work on it negative, which represents an energy loss from the system. All right, it's the system being the glider. So that's why that term is negative and that term is negative, and that equals what the work total by the work energy theorem, change in kinetic energy from last section, is. So again, let me stress, the work total equals change in KE. That is the total work. It is. Back in this problem, the only work there was on the spring was due to, or on the glider was due to the spring. There was no friction. So I just added in friction, right? Which is also a negative amount of work. All right, my goal is still to solve for D, but we have a little bit more complex of a formula. We have a D to the first power, a D to the second. Gonna have to use quadratic formula to solve. So we get everything to one side. I don't care what side you go to, just to have less negative stuff, I moved all these terms to the right, but it really doesn't matter. Doing that and plugging in all our givens so we can figure out the coefficients yields this formula. A, B, and C values are now showing, and I can plug into the quadratic. I get two answers out, and because we were looking for distances stretched to the right, the positive direction, this one has to be our correct answer, 0.086 meters. Now this should make sense, that I got a number in part B that is smaller than the number in part A. If there was negligent friction, this glider would slide further, right? Because there's less stuff slowing it down, doing negative work on it, right? In this case, just a spring is pulling back on the glider, and it goes to 0.106 meters from equilibrium position. But since friction is also helping it slow down and stop, in addition to the spring, now we don't go quite as far. So that should make sense. Okay, so I hope I defined everything clearly in that, especially with the signs and what each formula represents. So I'm now going to post this with an assignment for problems out of this section, and we only have one more small section really to go in this chapter.